Yep, one more lap. All right, today we're going to do Chapter 9, the ideal gas laws. Once again, much of this can be attributed to our friend Avogadro. First, we're going to review the kinetic molecular theory and how it affects physical state. Then we're going to do the pressure-volume relationship, that's Boyle's law. Temperature-volume relationship, that's Charles's law. The mole-volume relationship, that is Avogadro's law. We'll combine all of these and make the ideal gas law. And then we'll do ideal gas law calculations. Remember, please, the departmental assessment, 16 points extra credit, got to be finished by 4/12. That's their deadline, not mine. Please do this. It's a lot of points towards your 350 total. Also, I mentioned last week, this is Amnesty Weekend coming up. So, if you have tutorials from the first half of the class that you did not get a chance to finish, or you would like another attempt or so at quiz number 1, this is your time. It'll come on Friday morning. Both of these will wake up on Blackboard and will stay up all weekend. Yes. They will disappear midnight on Sunday. Any questions? All right. Kinetic molecular theory, we've talked about this before. Every particle in the universe seems to have an attraction for every other particle. Basically, that makes them lump together. A model of this collection of buckyballs, the little magnets that you feed to children, they're held together by magnetic force, which represents the attractive force between particles. This would be a solid. According to kinetic molecular theory, when you have a solid, the individual particles in the group do not have enough inherent energy, kinetic energy, to break the attractive force between them, so they just kind of sit more or less in one spot and vibrate. When you put more energy into the system, heat it up, you transition into the liquid phase. In the liquid phase, you have enough kinetic energy to bend the bonds, if you will, but not break them. So the particles just tend to slip and slide all over each other. That makes a liquid fluid, takes on the shape of its container, but it's still not compressible. Finally, if we put energy into the liquid, we move to the gas phase. In the gas phase, we have particles that move randomly, bounce off the walls of the container, off of each other. They have enough energy to totally overcome attractive forces. A couple things to note about the gas. First of all, yeah, they're just bouncing around like crazy. They move very quickly. They have lots of inherent energy. They bounce off the walls, and there's a lot of space in between them. We'll see that this bouncing off the wall is a very important part of the gas laws. To summarize what we know about atoms in the gas phase, it has an indefinite shape, takes on the shape of the container. Because there's so much room in between them, you can compress it, you can make the container bigger, that expands, and they diffuse rapidly and uniformly throughout the container. Samples from over here are the same as samples from over here. Any questions? Well, let's talk about the process of running into the walls of our container. This is gas pressure. Every time one of these little particles hits the wall, it loses a little bit of energy to the container. Now again, this is a calculation. This top thing here is floating, and literally what the calculation does is every time a particle bumps into it, it pushes it up a little bit. So it kind of pushes up and down, up and down. This is gas pressure. Now, these are awfully small gas particles. You would expect that they don't exert much, but that's wrong. Atmospheric pressure, the pressure from our atmosphere pushing down on us at sea level, is almost 15 pounds on every square inch. Now, a square inch, is like this, okay? It's tiny space, and it's a huge amount of force. There's a very dramatic demonstration of this. This is a burner that you use to fry turkeys and burn down garages and stuff like that. What we're going to do is take a 55-gallon drum, put a little bit of water in, seal it up, put it on this, heat it up. The water boils, whatever. Then you cap it up, and in this case, to make it go quickly, they're going to dump it into a little swimming pool of water, whatever. When it cools, the pressure inside the drum becomes less, and the 15 pounds per square inch still pushes on it from the outside. So it kind of looks like this. Here's our drum, a little bit of water, steam it up, seal it. Drop it in our little baby swimming pool. 30 seconds later, wow. Once again in slow motion, there it goes. The 15 pounds per square inch is sufficient to smash this barrel, just like that. We would all be smashed to nothingness if it wasn't for the fact that we have air on the inside pushing out with the same force. So, important to remember. Any questions? Temperature-volume relationship comes into play first here. The temperature of the gas inside goes up when we heat it. It decreases as the volume decreases, forcing the internal pressure to drop as Boyle's law. When the pressure inside drops, outside pressure wins, and you smash your barrel. Now, there are classic ways to measure air pressure. These are antique things. This is a lab manometer. We would fill this part with mercury, put this in the vacuum line, suck it down. When the two levels of mercury came very close, you could read the difference on a scale, and that would give you the pressure. This is a recording manometer with a little coil here that responds to pressure, makes a line. This is standard barometer sort of thing. And this is my favorite. When I was very young, I lived in Florida, and we had one of these guys sitting on a shelf. Okay, now this was the 50s. There was no such thing as a satellite going overhead looking for storms. Turns out that when a storm approaches, the pressure drops. Atmospheric pressure will drop. This is a sealed globe up here, and this one's open to the air. The more intense the storm, the higher the liquid would rise up in the little tube. And so this thing was sitting on your shelf. If it did this, you knew that something big was coming and it was time to Get yourself hunkered down. Amazing the technology we have now. It was much more exciting in the old days. In general chemistry, one of the standard experiments used to be to make a mercury barometer. Now, mercury barometers are still used. Basically, it's a tube about a yard long. You fill it with mercury. You have another little pot of mercury down here. When you make the tube upright, the weight of the mercury will drop. You'll get a vacuum here, and it'll stop when the air pressure pushing down on this equals the strength of the vacuum. Okay. This used to be a standard lab experiment. Everybody would take their glass tube, sealed at one end, and you would take a beaker full of mercury and kind of pour it in carefully. Then you would take a big beaker of mercury, put your thumb over the tube, stuff your hand under the mercury and let go, and you would make a barometer. Now, since mercury has been determined to be a neurotoxin, they don't do this anymore. We can't even have it on campus. But this was a mercury barometer, the good old days. The barometric pressure, the air pressure, was given by the height of the mercury column from the top down to the surface of the mercury here. That's H. As the air pressure increased and decreased, this would go up and down and up and down. Typically, we measure this in millimeters of mercury. At sea level, 0 degrees, 760 millimeters is defined as atmospheric pressure. Okay, height of 760 millimeters of mercury. We also refer to that as 1 atmosphere. 1 atmosphere is the same as 760 millimeters of mercury. Some places you'll see millimeters written as torr, T-O-R-R. I don't know why. As we said, 14.7 pounds per square inch represents this in the English system. We will not use this number. We will use atmospheres and millimeters. If you note, the conversion between the two is quite simple. They're related by a factor of 760. Simply multiply atmospheres by 760 to get millimeters. To convert the other way, divide by 760. 760 is your magic number. Any questions? All right, well, this brings us to our first gas law, the pressure-volume relationship. Here we're going to use this little device. It's a piston. It's all sealed up. Has a platform on the top and a gauge for measuring pressure. We fill it with a gas. All right. What we're going to do here is put something on top. The mass is going to push this down, and as it does, we will look and see what happens to our gauge. We will start off with a very small mass. And if you look, I didn't see the needle wiggle at all. So we have very little compression of our gas here. But if we transition to a larger mass, something like that, we have the piston going way down, the pressure going way up. This is an inverse relationship. That is, the higher the pressure, the smaller the volume. We'll see this is called Boyle's law. This is a little video demonstration of the process in slow motion. What we're going to do here is to slowly increase the pressure up here, pushing this down. Pressure will go up, volume will go down. Watch the video. We're starting off out here. Our pressure goes up, and the volume decreases. Just like the anvil, except not as exciting. The first thing you should note here is that this is a nonlinear relationship. You expect that, of course, because this can never drop to zero volume, can it? The particles themselves have an inherent volume, so it must be nonlinear. What you do is you take data from that curve and you plot it out. And sure enough, it is nonlinear. In fact, this represents a hyperbola. Now, chemists really don't like curves. Everybody likes straight lines, right? Mathematicians say if you have a hyperbolic relationship, you can linearize that by doing what's called a reciprocal plot. Reciprocal plot here would be plotting the volume against 1 over the pressure. When we do this, we get a very nice straight line going essentially through zero. Okay. Mathematically, our original curve here simply says that volume is proportional to 1 over P. Nice straight line. Okay? Whenever you have a proportion sign like this, mathematically, you can replace this with an equal sign and a constant. Equals constant, the same as proportionality. Turns out that the constant here is simply the slope of this line. We don't really care about that. But nonetheless, this describes the linear relationship with an equality. This is what is referred to as Boyle's law. We can rewrite this equation in a little bit more convenient form, get rid of the reciprocal, multiply both sides by P, and get PV is equal to K. That's where you want to go. Now, let's say we have our piston. We have two states. We started off with this guy, with the feather. Very little pressure. Nonetheless, for any closed system, this tells us that pressure volume is a constant. So we'll call this the initial state. P1, V1 is equal to a constant. Over here we have our compressed state. We have a small volume, we have lots of pressure. Nonetheless, because it's the same closed system, P2, V2 is still going to be equal to a constant. Now this constant is the same for both. If they're both equal to the constant, they must be equal to each other. We wind up with P1, V1 equals P2, V2. This is Boyle's law. Now, I don't really care that it's Boyle's law. I will never ask you about Boyle. This is what he looks like, kind of an arrogant Englishman. But nonetheless, this is Boyle's law. This is the pressure-volume relationship. P1, V1, P2, V2. Any questions? Inverse relationship, pressure goes up, volume goes down. Well, let's do a simple problem. We have a pressure of 12.5 liters is our volume. Our pressure is 0.82 atmospheres. We're going to change our pressure, so we're adjusting our little piston here. to 1.32 atmospheres. What's the final volume? So as we adjust this, the volume's going to change, the pressure changes. Again, P1, V1, P2, V2. We're looking for the final volume, that's V2. So let's take our standard expression and simply solve it for V2. P1, V1, P2, V2, simply divide by P2, and that's our expression now. Once we're there, all we have to do is substitute. P1 is 0.82, V1 is 12.5, P2 is 1.32. Atmospheres, top and bottom, they will cancel. We're left only with liters for our volume. 0.82 times 12.5 divided by 1.32. We're at 7.8 liters. This is pressure-volume relationship, Boyle's law, very simple problem actually. Do you have any questions? Well, then let's do another one. Here we have 150 mils of CO2. We're at 35 millimeters of mercury. We're going to decrease our volume to 50 mils. What's the final pressure? Now you'll note that in the first problem we had things in liters and atmospheres. Again, it doesn't matter because they're going to cancel. The units are going to cancel. Just make sure they're all the same unit. Once again, it's the P1, V1, P2, V2. We're looking for the final pressure. That's P2. So, take our expression and solve it in terms of V2. Simply divide by V2. Now we look at our problem. P1 is 35 millimeters, V1 is 150 mils, V2 is 50 mils. We substitute. Milliliters will cancel. 35 times 150 divided by 50, 106 milliliters. Now sometimes, just to be annoying, I will take a problem like this, and you will do a calculation like this, and I'll say, what is that pressure in atmospheres? How do we do that? Well, we immediately remember 1 atmosphere is 760, right? We have 106. We are simply going to take milliliters, divide by 760 to get atmospheres. If you have atmospheres and you want millimeters, you multiply by 760. If you're going the other way, you simply divide. This is 0.14 atmospheres. Any questions? All right, there are 3 tutorials in this chapter. The first one is pressure volume, and that's Boyle's law. When you work these, there are going to be some very simple metric conversions that you have to do. For instance, we have one volume in liters, one in milliliters. We have our pressure in terms of atmospheres. We're looking for atmospheres, so that's okay. When I do these things, the first thing I do is make a little list of what I have. I know I'm going to do P1, V1, P2, V2. So I make a list. P1 is this, P2 is that, B1, whatever. We're looking for P2 in atmospheres. We have atmospheres, that's good. Our initial volume here was 550. So what I did is I changed V2 from liters to milliliters simply by multiplying by 1,000. I could have divided this by 1,000, doesn't matter. So, Boyle's law, P1, V1, P2, V2. We're looking for P2, that's P1, V1 over V2. Simply substitute, do your division. Calculator gives you 4.538. We look up here, by George, we only have 3 significant figures, so let's round this to 454. Any questions? All right, let's do another one. I will hush for a minute, and you go ahead and set this up. Our pressure is initially given in millimeters. Our final pressure is in atmospheres, so you have to do that conversion. This is given in milliliters. We want the volume in liters. So 2 simple conversions here. Make your list. I change B1 to liters. P2 from atmospheres to milliliters. It's your choice which one you want to do. We do this simply by multiplying by 760. So set it up. And again, we're looking for V2. Well, with the simple algebra, V2 is P1 V1 over P2. We simply look at our table, substitute in. We get 3.575 liters, 3 significant figures, and there we go. Any questions? Straightforward, Boyle's law. All right. Temperature-volume relationship. Here we are dealing with the effect of temperature on the resulting volume. We're going to do a fun experiment first. We're going to take this poor balloon that's just sitting here, and we're going to dump liquid nitrogen all over it. Now, liquid nitrogen is very cold, minus 196 centigrade. Very cold. It's going to cool down the air inside the balloon very rapidly. We expect, as it cools, the balloon will collapse. So, here we go. Here's our poor balloon showing a little anxiety. There's the fun part. And sure enough, as we cool this thing down, the balloon collapsed down to nothing. Not only that, but as it warms up, it slowly reinflates itself as the pressure inside grows, and pretty soon we're back to its former glory. It's a simple linear relationship. Temperature decreases, volume decreases. Temperature then increased as it warmed, and the volume increased. We predict this should be a simple linear relationship. Now, playing with balloons is fun, and liquid nitrogen is really fun. But chemists like to be a little more systematic. So what if we took a known number of moles of gas, so that's a known volume, and we slowly adjusted the temperature way down here and monitored the volume? We predict that this should be a linear relationship. So let's start off with just a little bit of gas, 0.25 moles. Take it to 200 degrees, measure its volume, 100, 0, minus 100, minus 200. Yep, this is linear just like we expect. But, again, chemists can be a little compulsive. You don't want to risk everything on a single line, so let's do it again with half a mole. And sure enough, it's still linear. 0.75 moles. Yep, nice linear relationship. But I want you to look where these lines are all pointing. They all look like they're kind of going to the same place, don't they? In fact, if you take these lines and you extrapolate them down, they all intersect at exactly the same point. This would be minus 273.15 degrees centigrade. At that temperature, this plot tells us that the volume will be 0. Now we know it can never really be 0, right? It can't be 0, but the extrapolated value here is 0. This magical point here is what is referred to as absolute 0. It is also defined as 0 on the Kelvin scale. The Kelvin scale is simply centigrade minus 273 centigrade. So we're 0 and we go up on our Kelvin scale. Whenever you do a gas law problem involving temperature, you must convert centigrade to Kelvin. It must all be done in terms of Kelvin. We'll do the conversion in just a minute or two. First, let's take this relationship and look at it mathematically. With our linear relationship, we said that volume was directly proportional to temperature. Temperature goes up, volume goes up. Temperature down, volume down. Direct relationship. We change our proportion to equal in K, and we get this. Now, once again, we want to isolate K. K is equal to V over T. Now, with our balloon, we had two states, just like with our piston. When we were at low temperature, V1 over T1 was K. When we were at higher temperature, V2 over T2 was still K. And the two Ks are the same. Same balloon, same gas, same everything. That means we can equate these two, and we get V1 over T1, V2 over T2. This is what is known as Charles's law. Now, Charles was his last name. And unlike Boyle, he's kind of a nice-looking guy. First time I saw this picture, I don't know if anybody still remembers Barry Manilow, but yeah, it's kind of a dead wrinkle for Barry Manilow. But nonetheless, a nice looking guy. He was a balloonist. He was the first person to actually hop in a hydrogen-filled balloon and fly over the French countryside. This was his balloon, something like this. He filled it with hydrogen, made the hydrogen by taking iron and reacting it with sulfuric acid. It's a single replacement reaction, isn't it? Hydrogen is acting as a metal. Metal replaces metal. We get H2 gas and iron 2 sulfate. Filled up the balloon, yep, nice and full. Put a little gondola on it and took a ride. The wind blew him gently over the French countryside. And I guess the view was thrilling from up there, probably a quarter-mile high. Nice view, nice ride. And he's floating around and he sees this little village and says, okay, I've had enough. I'm going to come down, go there, call home, have him come pick me up. So he starts descending from the sky. Now, peasants in a French village in those days had never seen something descend from the sky with a guy in it. And they kind of like reacted as you might expect French peasants to do. Well, they attacked it with pitchforks and knives and whatever. Fortunately, Charles lived, but nonetheless, it's a good thing, however, that they didn't do the other thing that French peasants were known for, and that is throw torches at it. Because hydrogen, as we've seen, is very flammable. Hydrogen is also a very, very nice substance to use in a balloon because its density is the least. In the 30s or so, this was exploited a lot. This is the world's largest dirigible. This is the Hindenburg. And this was actually built first for propaganda reasons, and secondly, to serve as a transport across, back and forth on the Atlantic Ocean. So people would be down here, there are big bags of hydrogen in here. You sit down, you relax. 4 days later, you're in New Jersey. However, on its maiden flight across the Atlantic after 4 days, as it approached New Jersey, there was a thunderstorm. The thunderstorm created a static charge on the surface of the balloon. As they vented the hydrogen to come in for a landing, it exploded. Hydrogen for balloons kind of fell out of favor after that. Little too dangerous, terrible explosion, lots of people killed, whatever, very dramatic photo. Any questions? All right, well, we talked about Kelvin and centigrade. Remember, another magic number is 273. 273 plus centigrade gives you Kelvin. A word to remember, a thing to remember, because we're adding to centigrade. Centigrade is always a larger number than Kelvin will be. Always a larger number by 273. So if we're at 1,000 centigrade, we're simply going to take 1,000 centigrade, add 273. We're at 1273 Kelvin. Minus 150. Add 273 to it. 123 Kelvin. 100 degrees, that's the boiling point of water, right? Water boils at 100 centigrade. It boils at 373 Kelvin. Remember, you have to always convert centigrade to Kelvin whenever you do a gas law that involves temperature. So let's do one. We have 50 mils of gas at 26 centigrade. We heat it at constant pressure until the volume is 62. What's the final temperature? A classic volume temperature problem. Again, we're going to use Charles's law. We know V1, we know T1, we know V2, and we're searching for T1. That should be T2. You know, I always forget to change that slide. That should be T2, of course. All right, here's Charles. We're solving for T2. To get T2, we have to multiply both sides by T2, then divide by V2. We wind up with V2 T1 over V1. Simple cross multiply. Now, let's substitute, but before we do, we realize this is in centigrade, it must be Kelvin, right? So we will take this and we will add 273 to it. We get roughly 300 Kelvin. So let's substitute 64 mils, that's V2, our final volume. That's our temperature, T1, and our initial volume here, 50 mils, V1. Milliliters will cancel. 62 times 300 divided by 50. We're at 373.84 Kelvin, but we have three significant figures, so let's round it to 374. Okay. What if I asked you what this was in centigrade? Sounds like the kind of thing I would do, right? You would simply take Kelvin, you would subtract 273, and you would get 101. Any questions? All right. The second tutorial. If the first one was Boyle, it's only fair that the second one is Charles. Now, once again, you're going to have to do conversions between centigrade and Kelvin, milliliters and liters. Again, we want our final temperature here in Kelvin. Blackboard looks exactly the same. So, again, I would start off by making a list. On my list, I would put T1, V1, T2, V2, and do whatever conversions I needed to do. We are given a temperature in centigrade. Let's change that to Kelvin by adding 273. We're given both milliliters and liters. Let's change them both to mils just because we can. We could change that to liters the same way. So now everything is constant units, and we're simply solving for T2. Take your equation, cross multiply, separate out T2. V2 T1 over V1. Substitute in. This is milliliters are going to cancel. and we're going to get our temperature directly in Kelvin. 264 is what you should get. Any questions? All right, so that's tutorial number 2.
379.041.
This guy, this is 106 plus 273 to give you Kelvin. It must all be in Kelvin. All right, let's go back to our plot. Now, you know, doing this experiment in the lab is a bit of a pain in the butt. It really is. Because, well, it's just difficult to do all these measurements and stuff like that and collect all this data. So once you get a plot, you try to get everything out of it that you can. We defined absolute zero down here, that was good. We confirmed our linear relationship, that was good. But what if we just picked any old temperature? And we asked, what's the relationship between the volume and the number of moles? Now again, intuitively, you would think the more gas you push in, the bigger the volume. And by George, your intuition would be correct. If we take these data and we plot them out, we get the mole-volume relationship. The dependence of volume on the number of moles. Once again, intuitively, we expect this to be linear, and by George, it is. This is the ghost of Avogadro, and is called Avogadro's law. The more moles you have, the bigger the volume. Kind of intuitive these days. At the time, it quite wasn't. All right, so we have 3 simple gas laws. Pressure volume, temperature volume, mole volume. Let's look at these 3 proportions. Volume proportional to 1 over P. Volume is also proportional to T. And volume is proportional to N, where N is the number of moles. Well, mathematically, if volume is proportional to all of these guys, we can combine all of these together and make this. Volume should be proportional to the number of moles times the temperature divided by the pressure. Now we can do our trick. Change the proportionality sign to an equal and a K, and we get what we will refer to as an ideal gas law. Now the only problem is I'm really tired of K. Use K a lot. Instead of using K, I could use anything, right? So I say I'm going to use uppercase R instead of K, and I'm going to call it the universal gas constant. V is equal to R times Tn over P. Well, that's a fine equation, but you know what? It doesn't quite flow off the tongue. Not a nice thing to say. R, T, N over P. What if we took and multiplied both sides by P? Get this out of the denominator. We would get this. Now this is a nice equation. PV equals nRT. It kind of like rhymes. It has a nice sound to it. PV equals nRT. This is our ideal gas law. Think about it. If we know three things here, we can always solve for the unknown. Only problem is, this is our constant, right? What the heck is our constant? We need a number. How in the world are we going to do that? Well, to do that, you have to talk to your friend Avogadro again. Remember, he determined that 1 mole of any gas at 273 Kelvin, that's 0 degrees, 1 atmosphere pressure, and a volume of 22.4 liters. So, we know our pressure, 1 atmosphere. We know our volume, 22.4. Number of moles, 1. Temperature, 273 Kelvin. Solve this for R. PV over NT. Well, that's clever. Substitute. 1 atmosphere, 22.4 liters, 1 mole, 273 Kelvin. Now at this point, I would typically click the little button here, and red arrows or red X's would appear, and they would cancel, right? Nothing cancels. Nothing cancels. So, okay, we say fine. We take 1 times 22.4 divided by 1 divided by 273. 0.082057, and the units, lovingly, are liter atmosphere per mole per Kelvin. Now, I can never remember that. I can't remember that to save my life. But anytime that you need to know a value for R on a problem or quiz or whatever, I will give it to you. Okay? Don't worry about it. I will give you a value for R. So let's see what we can do with PV equals nRT, the ideal gas laws. We're looking for the number of moles of argon in 18.6 liters at 293 Kelvin, a pressure of 2.3 atmospheres. PV equals nRT, and we're looking here for the number of moles. So we'll divide both sides by N. N is PV over RT. Okay, substitute in our pressure, 2.3 atmospheres. Our volume, 18.6 liters. R, it's a big number. T, it's a little number actually, lots of digits. And T, 293 Kelvin. There's our pressure. There's our volume. There's R. And here is T. We see that we can immediately cancel atmospheres. We can cancel liters. We have Kelvin and 1 over Kelvin. Those also cancel. And we're left only with mole to the -1 in the denominator. We know that that comes up. So we just calculate 2.35 times 18 times divided by 0.018 divided by 293. We have 1.81 moles of gas. PV equals nRT. Remember it, it's fun to say, fun to remember, PV equals nRT. And our last tutorial for this chapter is basically PV equals nRT. Ideal gas law. Gas system has volume, moles, and temperature of this, this, and this. What's the pressure in atmosphere? So we're solving here for P. Once again, with all the gas law problems, first thing I do is make a little table. Our temperature is in Kelvin, that's good. That's number of moles, that's N. And our volume is liters. The pressure will automatically come up to be atmospheres. No conversions necessary. We're going to take PV equals nRT and solve it for P. As we do that, P is nRT over V. nRT over V. 1.86 is our answer. Now, occasionally this will come up, and instead of asking for atmospheres, it will ask for millimeters. How would you convert this to millimeters of mercury? 1 atmosphere is 760. So 1.86 is 1408. Let's do one more. Let's address a burning issue first, though. Why are these called ideal gas laws? Because they're based on the notion that gas particles are free spirits, they bounce around, they have no attraction for each other. That's wrong. Sometimes when they come and collide, they stick for just a second. Actually, much less than that, but nonetheless they stick, then bounce away. There is a correction that you must do at very, very high pressures. But at traditional pressures and temperatures, this works. Ideal gas. All right. We have pressure in atmosphere. We have a volume in milliliters. And we have moles. We're looking for temperature in Kelvin. Only thing we have to change here is milliliters to liters. So make your table. Go ahead and set it up. Solve for T. And calculate our final temperature.
Why did you change it to liters?
I'm sorry?
Why did you change it to liters?
Remember R. R isn't shown here yet, but R is in liters. It's in liters and atmospheres, kelvins. So you need those. All right, so solving for T. PV over nR. We have a pressure. We have a volume in liters. We have R. And we have number of moles. Simply do our math. We're at 225 Kelvin. If we wanted this in centigrade, what would we do? Centigrade plus 273 is Kelvin, right? So Kelvin equals, or so centigrade equals Kelvin, minus 273. All right, let's look at some simple exam questions. As you probably have realized by now, on occasion I put things on exams that I think in my head are really easy so everybody gets one right, makes them feel good, whatever, okay? I put this on. Actually, a different version of it, but nonetheless, I put it on, thinking everybody would get it right, and virtually everybody in the class missed it. So it has become a staple on my exams to ask either Charles or Boyle in this format. So make sure you understand this. Which of these truly is Boyle's law? Well, as we look at them, first one, P1, V1, P2, V2. By George, that does have a familiar ring, doesn't it? That's our definition of Boyle's law. How did we get here? We got here because PV, we said, was a constant for our initial state and our final state. So this is where we started. Yeah, that's Boyle. And if you take this equation and you fiddle with it, you can rearrange it. P2, P1, V1 equals P2, V2. Yep, you can do that. So, actually all three of these work. This is an all of the above. So the next class, I didn't do Boyle, I did Charles. Which of these is Charles's law? Well, on your 3x5 card, I hope you have written down Boyle's law, Charles's law, okay? Just to refresh your memory. Charles's law looks like this, V1, T1, V2, T2. But they're divided. They're not multiplied. That smells of Boyle, doesn't it? This guy is wrong. Temperature volume is a constant. No. We said volume over temperature was a constant. That's wrong. So can we take this guy and mathematically figure it, fiddle with it, and get it into this shape? Nope. No matter how you do it, you can never get T1 over T2, these guys, and V2 over T1. Doesn't work. So this is not all of these, this is none. In addition to the mind games, we also do problems. We have 450 mils of gas at 1 atmosphere, and the volume is reduced till the pressure is 5 atmospheres. What's our final volume? This is a pressure volume, isn't it? So that is Boyle. P1, V1, P2, V2. We're looking for our final volume. That's V2. V2 is going to be P2 at 450, 1 atmosphere, 5 atmospheres final pressure, atmospheres cancel, 450 divided by 5, 90 mils. All right, one last one here. When you are comparing degrees centigrade and Kelvin, which of the following is true? 1 Kelvin represents a larger temperature change than 1 degree centigrade. Actually, we addressed that back in chapter 1. No, they're exactly the same temperature change. 100 kelvins is 100 centigrades. Celsius and Kelvin are never numerically equal. Well, of course they're not. Because to convert centigrade into Kelvin, you have to add 273 to it. It's always 273 bigger. They're never numerically equal. That's true. Our last one, readings in centigrade to be converted to Fahrenheit. Oh my goodness, how stupid is that? We could do conversions all day, but we'll never use Fahrenheit. I promised you that a long time ago. They're never numerically equal. They always differ by 273. Are there any questions? Now you see chapter 9 was fairly innocuous. The math, a tiny bit tedious but not crazy. Our gas laws. Gases are in constant and random motion. Yes, they are. Pressure arises from collision with the container walls. Yes, they do. No attractive or repulsive forces exist. Collisions are truly elastic. Ideally, that's true. It's not quite true, but it's true enough. The volume of molecules is negligible. Yeah, it is pretty much negligible compared to the volume of a gas. The gas laws can be thought of quite intuitively by a series of 3 little video clips. Let's listen to them.
If the number of gas molecules in a container is doubled with no change in the temperature or volume, the number of collisions between gas molecules and the container walls doubles, which translates into a doubling of pressure.
This is Avogadro, right? We increase the number of moles, we increase the pressure. Number of moles goes up, collisions go up, pressure goes up.
If the temperature of a constant volume of gas is increased, the molecules of the gas move faster, and each collision exerts a greater force on the walls of the container. In addition, because the molecules move faster, the number of collisions between gas molecules and the container walls increases, and therefore, so does gas pressure.
You heat it up, they move faster, they'll run into the container more often, with more energy, temperature goes up, pressure goes up.
If the volume of a container of gas is reduced by half, but the amount of gas remains fixed, more collisions will occur between gas molecules and the container walls in a given time, leading to an increase in the force exerted on those walls.
If we take and we make our volume smaller, we will get more collisions per unit time. Collisions equate directly to pressure. So this is the intuitive version of the gas laws. Any questions? All right, we added 3 tutorials: Boyle, Charles, and ideal gas laws. We have quite a list now. Some of you have done them all. I admire that. Some of you haven't. I prefer that you do them all. Remember, you're shooting for your 350 points. Also, remember the assessment is due on the 12th. This is 16 extra credit points that again contribute to your 350. Don't blow those off. About half of you have finished this, gotten full credit, other half haven't. Please do that. And finally, the announcement of the day. Amnesty Weekend. Friday, Saturday, Sunday, tutorials from the first half and quiz 1 are both open on Blackboard. They will close up again at midnight on Sunday. This is your chance. If you miss tutorials in the first half, do them. Are there any questions? All right, I will see you Wednesday, I hope. Oh, speaking of lab, some of you haven't done lab 9 yet. It's online. I know it's a little painful to listen to me, but listen to me. I tell you exactly how to do the quiz part, then do the quiz part and get your 10 points.
What folder is it for to listen to?
Yeah, I like it done like yesterday, but soon. Okay, try to do it soon.
Where do I go to listen to your video?
It's right there. It's labeled intro video and then lab quiz portion.
Okay, thank you.
Okay.